Good evening and welcome everybody. This is Obi-Wan Piz for Simplex Pachinko. We are back. Those of you who were in earlier, thank you very much for coming. We were doing an organization type stream. I was talking with Zach over at Eat of the 2i Pie earlier. And I came to the realization that, like, hey, this was actually a success, not just because we passed our goal of 420 viewers, because of course we selected that number. Not only because we got, you know, a lot of stuff done, but I think I came to the realization that having a, like, entertainment stream of me not actually talking with people and just doing stuff kept me kind of accountable. So we may have some more of those in the future. Just like doing random housework, because goodness knows I need to be held accountable for it. So I hope everybody's having a good Tuesday. That's what this is, yes. Hope everybody's having a good Tuesday. And we're gonna get on with some more mathy type stuff. We were working on a average. Somebody was talking about the average of, what was it? Yeah. If you have these blue points which fall on a parabola, and then you take a bunch of tangent points which touch the parabola only at that exact point, and then draw a line otherwise, and then do that for all 5 of the points, then the intersection points for all of those points have an average x value, which is the same as the average x value of the blue points. So our blue points and our orange points have the same average. So I went into this kind of blind and didn't know what to do here, but I wanted to prove it like a little more rigorously. I know a couple of people came in and said, like, you know, Megalomorph, I think, was like, well, yes. We're just doing a transformation, so, like, of course it's going to be that. I was like, that's, you know, that's fine, and obviously the book that I got this from said that this is the result that we're supposed to get, but I wanted to do it from, like, my perspective as a trig and pre-calculus teacher. So from a pre-calculus perspective, this took a lot of algebra, but we did it. We said, all right, so each of these individual lines, without loss of generality, we could let it be line 1, line 2, or any of the 2 lines that we pick, as long as they're not the same as each other. And we wanted to find where they intersected. So we found the x value where those things intersect. And it's really gross, but it's the sum of their individual blue point x values minus the c value from the shifting. So how much the parabola was shifted. And again, sure, you could have this not be shifted, but, like, I want to show that this actually works. Minus our slope between, so this is the secant line between those 2 points, and then times 1 over 2a, the steepness of the parabola, twice the steepness of the parabola. So then we said, let's do that for any 2 points, and it's just going to be this, which that should be the other one. M and N. There. Now we said, we're just going to do that. Hey, everybody. Thank you, Zach. Thank you, everybody, for coming on over. Ah, I've been invaded. Danny, corrupt converter, how's it going? And we looked at the individual, we said that the average of all of those individual intersection points of the tangent lines of each of these things on that parabola ended up having this really big equation, or expression, which then when we broke it down, these ended up being all this stuff cancels out, makes it very nice. Everything all gets knocked down into these forms, and eventually it was that, sure, if we take the sum of all of the individual x values of the points that were on the parabola, and then we divide by how many points there were, we end up getting x bar, which is the average of the intersection points as well. So that was like, it took a long time to get there, but it's really cool still. So all of our orange points here, which are intersection points of the tangent lines from this parabola, have the same average x value as the blue points, which are the actual points on the parabola. Which again, yeah, okay, it makes sense, like intuitively, but I just wanted to make sure. Pen Center! Thank you very much for those bits, and thank you everybody for coming on over. My name is Obi-Wan Pez, this is N-Simplex Pachinko. We were on earlier today doing some organization of the office, and I was saying that, you know, it actually kept me kind of accountable. Because I was like, I have to make this, like, you know, I have to perform organizing. So instead of sitting here and watching YouTube all day, I actually got stuff done. It was nice. Although I will say I can get rid of this giant stack of boxes right here because one, you don't need to see the giant stack of boxes, and two, it kind of has my name on it, so woo. I'm sure it was slightly out of frame. It's fine. Oh. So anyway, how was everybody's day? We'll just get rid of these. This is one of those knives that's just sold at, like, Craftsman, but you were most definitely not supposed to carry it around on the streets of England. They have some pretty strict laws over here. But yeah, let's see. I was thinking about going to a karate class, and it was like, yeah, you probably don't want to carry your bow staff around. I was like, oh, great. And they're like, yeah, you probably don't want to carry a knife around that, like, doesn't have either A, a specific purpose, or B, is just like, you know, a little tiny thing like this. Yeah, accountability. Am I Ewan McGregor? I mean, to be fair, right? I do have the Pez dispenser. This is like that Simpsons episode with Mr. Sparkle. It was 100% most definitely an accident that they just happened to use my likeness. If the Pez company wants to sponsor me, let me know. I also enjoy Necco wafers. Remnants of cardboard. Yay! So anyway, how's everybody doing? Tonight we've got poke around in the same Math AMATYC Educator. We got solutions that went to like previous month's problems, but I could just look at the questions and take those, and then we can actually get an answer like in short order if I just don't look at it. That's fine. I got post-its. I can probably just slap one on there. And otherwise, if anybody has any actual questions, I will be happy to entertain those. I was pretty happy. I found my Mark Halpin, and I immediately spilled coffee on it. Yay. Found my Mark Halpin puzzle hunt. So he does one every year for Labor Day. So if you have time on your Labor Day weekend, you can check out the new one. And if you want to check out his other stuff, like all of the previous puzzles and puzzle hunts that he has made, he also has a website that I most definitely know what it is offhand. There it is. Alrighty. So if you have any particular interest in it, I would definitely check it out. Like I said, every year he does every year he does his own puzzle hunt on the website for Labor Day, and it's usually a really interesting, like, let's take some stuff about like the within the mythology of this particular group, and like kind of throw it out there and be like, hey, well, this is really cool, check this out. And he likes to use mythological figures, especially for, at least for that puzzle hunt. So he's been doing it the last few years. This year he also, or this past year, he also mentioned, hey, so I created this puzzle hunt months before the volcano eruption on Hawaii, so if anybody would like to donate to this fund, you know, I'm not just opportunistically using their culture. It was already planned, and then disaster happened, so terribly sorry, but please go see this fund. So he's been trying to coordinate with people on the ground over there to help the was it Hilo? Help the situation of the people on Hawaii. That is a weird question. All right. Oh, I skipped something. Boy, that completely makes a lot more sense now. All right, much better. Ah, okay. Okay, I get it now. All right, so consider 3 consecutive positive integers, one of which is prime, another of which has exactly 2 prime factors, and another of which has exactly 3 distinct prime factors. So examples 69, 70, 71, or 105, 106, 107. Are there any impossible ways for ordering those features? So can we not put, for example, the one that has exactly 2 prime factors in the second spot when the other that has exactly 3 distinct prime factors is in the third slot, or something like that? Right, so if we make these out to be like, you know, ABC. We want to know, like, can any of them just not be prime in the first place? If they are, again, in order. So it's not really just ABC, right? It's going to be A plus 1, A plus 2. And I'm guessing these are proper factors, so again, we're not counting 1 or itself. It's just going to be the factors which are less than it. And again, 1 is not prime, so. With exactly 3 distinct prime factors, this makes me think it's not true. Never mind. I was thinking like, oh, it has to be a square, but no, because neither of these contain a square. So never mind. So in this case, right, we've got 69 is the product of 13 and... Nope. Damn it. 23. And 3. So 69 is going to be the 2 prime factors one. Uh, 71 is prime. And 70 splits into 5 and 14, which is 2 and 7. So the prime factorization is 257. Which has 3 distinct. Oh, I'm off the bottom again. Right. In this case, 107 is obviously the prime. Because 105 can't be prime, and 106 definitely can't be prime. Alright, this is going to be 5 and 21, which is then 3 and 7. So 357. It's going to be our 3 distinct. And 106 is going to be 2 and 53. 53 is itself prime. The fact that the one that says 2 prime does not contain the word distinct made me a little concerned, but in this particular case it hasn't utilized any sort of like trickery, I guess, to get there. I don't know what I'm thinking exactly. Like if it was like 8, right? No, I mean that doesn't work either. Never mind. 4? No, 8, right? Because 8 can break into 4 and 2 and 2. So technically that's like... Never mind. No, that's only... Wait. That's only 1 prime factor. It's 2. But, never mind. Man. Okay, like 24, right? Breaks into 8 and 3. And then 8 breaks down into 2, 2, and 2. So technically it's only got 2 prime factors, 2 to the 3rd, and 3. But I'm not sure that that's what they would allow. But this is not really the point of the question, right? The point of the question is, can we prevent any particular ordering of those properties? Okay, so... All right, we know for a fact that one of these must be 2. Well, that's not... Hang on. No. No. In theory, right, we could potentially have 2 even numbers. I suspect it's not going to happen, but that's only because we're just given 2 examples where it isn't. And also one of them, exactly one of them, must be 3. You know what, let's put that on its own line. Exactly one of those P0 to P5 must be 3. Which means this is going to fall into the same sort of routine that we worked on last time with something. So, all right, P0 mod 2 is equal to 0 or 1. Nope. Product. Wait. Hang on. P0 mod 2 can only be 1. Right? Because it can't be... If it is a prime, right, then it can't be divisible. Wait a sec. Alright, that's the only possibility. In general, right, our product of primes could then be either it's odd or it's even. It doesn't really matter. The prime numbers would just have to be both odd in order to get a product that is odd. Or we could have 2 times any other prime number to get an even. So that's okay. And same thing happens with the product of 3 primes, P3, P4, P5. Any one of them is 2, and it has a divisibility of 0, or, well, it divides, 2 divides it evenly. And if they're all odd, then we just get a 1. That's fine. But right, unless P0 is equal to 2, but then 3 is consecutive and has no prime factors. Oh. Oh. Do we just hiccup? Did we just hiccup? How y'all doing? Alright, I'm back. Everybody else back? Okay. So P0 cannot be 2. Okay. And that is independent of the position of our three numbers, right? So it doesn't matter if we're talking the first, second, or third one. At least one of them must be, at least one of those prime factors must be 2 somewhere in it. It could either be, okay, nope, okay. Right, never mind, we're good. I'm okay, nope. So if A right, if these are both even, then A plus 1 must be the prime. Right, if these two are even, then the middle one must be the prime. Okay, now that's also a question we can bring out to the other side and say, like, is there something special then that has to occur between the two other things? So the product of 2 primes versus the product of 3 primes. So we got to go the same route on the next part, except with mod 3. So in this case, we could either have it be 1 or 2. Again, P0 is not going to be 3 itself. Konstantinos, thank you for the follow. Very appreciative for everybody who comes in and says hi and all that. So, and anybody who's hanging around, feel free to lurk. You know, we're very lurker friendly and learner friendly. So, anything that you would like, anything you want, anything you need, let me know. Or just hang out. Hydrate. Why, thank you. I do, in fact, I did just finish my coffee, so. It's probably a good idea to keep hydrated. Okay, so similar argument to above. We say if P0 is equal to 3 itself, then nope. 4 is the next consecutive integer. Which has only 1 prime factor. 2, right? So again, P0 just can't be 3. So we need larger prime numbers that have these particular behaviors. Alright, and it was helpful that they gave us 2 examples, 69, 70, 71, and 105, 106, 107. Okay, so if our prime number, whichever position it's in, if our prime number, mod 3, is 1 or 2, those are 2 possible options, then our, P1, P2 product, mod 3, could be, right, if P0 mod 3 was 1, that could have been in any of the 3 positions. So that means that if it was first, then our product P1, P2 could either have a modulus with 3 equivalent to 2 or 3. Or 0, right? 2 or 0. If it was in the second position, then its modulus could be either 0 or 2. And if it was in the third position, it could be either 2 or 0. So yeah, it's just going to be, okay, it's either 2 or 0. Right? If if modulus is 2, then it's going to be the other 2 again, so it's either 0 or 1. We don't know how it's exactly going to work, but that's how it's going to work for us at the moment. If P3, P4, P5, we test its modulus. If this is great. If we had a 1 and a 0, then its modulus would have to be 2. If we had a 1 and then a 2, its modulus would have to be 0. Oh, wait. No. Hang on. We're good. We don't need that one. Right? If we had a modulus of 2 and 0, this one would have to have a mod of 1. And then a 2 and a 1, it would have to have a modulus of 0. Right? So we see all 3 options represented in both of these other cases. So we don't know exactly what's going to happen, but we do know that at least one of them needs to be divisible by 3. Sorry, exactly one of them needs to be divisible by 3, and it can't be the prime. And then we don't have any particular ordering. Now, those things could be the same number. Where the one that's divisible by 2 is also divisible by 3, in which case it is most likely a prime times 6, rather than 6 itself. So let's just double check this, right? So if we take these two together, right? Can P1, P2 just be equal to 6? I suspect not, but let's prove it, right? So if P1, P2 is just equal to 6, then that means that the next numbers up or back, right? If we had 5, we cannot possibly have 7 as well. Then we'd have to have 4, but again, this only has one distinct prime factor. So that's out. Right, this is out. 7's out because it's also prime. So we cannot pick anything with 5 if we also pick 6. So then the only possibility here is 6, 7, 8. 8 only has one prime factor as well, which is also 2, so we can't use that. So P1, P2, the one that's two prime factors, cannot be 6. Good to know, sort of. Could it be, in theory, right, P to the first, to the P sub 1 to the M times P sub 2 to the N? I think it's against the spirit of the question, but I don't know that it's excluded. Right? Has exactly 2 prime factors. I don't necessarily take that to be those are the only possible factors of that number. Whereas in our examples, that was actually the case, right? 69 only broke into 23 and 3, and 106 only broke into 2 and 53. If anybody has any insights, suggestions, questions they'd like to ask, whether that be about this or something completely different, feel free to ask. I'm open to any distraction. I could check the... That's not really helpful either. It's an interesting like sub question that I'm trying to ask to myself, I guess, is that like it's not, this was not given in the original concept of can the outside numbers be even, right? And therefore would the middle number be prime? Hum. Having been a math teacher for the last 15 years also, if anybody has any, well, I guess technically 16 and a half, 17, something like that. If anybody has any particular, like, misconceptions or questions about something they don't quite understand, like, absolutely ask anything you want about that too. I did teach anything from basic algebra all the way through differential equations, and I have content knowledge that goes into a lot of the undergraduate and then graduate level mathematics classes, specifically heading up to differential equations and partial differential equations. I don't remember a huge amount of the partial differential equations, but that's my own problem. And I also have been trying to get back into it, at least somewhat. So I do have my, yep, it's down here. Do have my PDE Shams for if anybody does want to poke around in that. Not to say that I'm very good at it, but you know. It exists. Yeah, and I printed out a whole bunch of notes from a PDE book that somebody gave me. I was like, oh, you gotta check this out. It's actually good. Apologies. I am just getting over a cold, and I've been having allergy stuff, so all of it combining, it's just fabulous. Love it. Alright, I'm actually going to break out my old linearity book that came from the University of New Hampshire. This particular one was taught by Dr. Kelly Black of the university. He was he's moved on to whatever now, but Oh, I probably shouldn't have done that. There we go. In case we want to come back, you know. He was working on how to teach the students who had gotten into differential equations. Sorry, no, the students who had gotten into like the studio class, which was our calculus 1 and 2 combined into 1, and also taught alongside physics 1 and 2, and it was team taught. So both the physics professor and the calculus professor got together and talked like the entire semester about how to coordinate what topics were being taught when. It was a brilliant class. I should have probably opted out and just taken my AP credit of, you know, a 4 on the exam and just been like, yep, I'm going to go right into differential equations. But instead I opted to take the studio class, which I must say was pretty brilliant, and I loved doing it. Our professor was Dr. Gertrude Kraut, who was a lady whose family came over from Germany, escaping Germany, shall we say, in the 1940s. She was a very remarkable lady, and I loved hearing her talk about all sorts of stuff. Mathematical, because she most definitely did not talk about her family's past. It was pretty rough. But they escaped. They made it back. I think they said they made it through England and then back over to the U.S. She confided, or, you know, not like, she just got into more conversations with several of her students. I was not one of them because I was not particularly good student, I must say, in that sense at least. I will say, like, if anyone is wondering what to do with your college professors and be like, oh no, they're so intimidating, like, no. Go talk with them. Just realize that they are human, and, you know, if you would just want to talk about like college in general or your life, what's going on outside, they'll be willing to hear you out most of the time. Just don't think of it as like, I want an excuse to be late, because that's not going to work. All right, I'm going to put on our 3-minute ad break to go cycle some water, and I'm going to set up the next problem. I'm just going to start like in on this thing. So I'll tell you more about what linearity was as a class and what Dr. Kelly Black was all about. And yeah, just be back in a couple minutes. Thank you so much for sticking around, and hope to see you in a few minutes. Hey everybody. Okay, entered night mode. So turn down our ambient lights here. So I got this one as the major light. You'll also notice over here that is what it looks like at 10:10 p.m. So yeah, she light outside. I hadn't really thought about it that much, but yeah, it turns out we're also like close enough to 6 degrees away from the Arctic Circle. I hadn't really thought about that, but like, that's a thing. And of course I leave my water in the other room. Cool. Don't mind me. Just be right back. Singing my Getting the Water song. Okay. So anyway. So Dr. Gertrude Kraut was my calculus professor. I haven't actually found out what she's up to. I assume she's retired at this point. It's been 23 years, essentially. Yeah, she and Dr. Simpson, I don't remember his actual first name, but Dr. Simpson was our physics professor. Got the physics and the calculus worked out really well, and we would usually, it was like Monday, Wednesday, and Tuesday, Thursday, we would go to whichever room it was we were supposed to go to. I don't remember. I think Monday, Wednesday was calc, and Tuesday, Thursday was physics. We go to the appropriate building, which were not in the same place. And then on Friday, it was sort of a switch. Like, you go to one, and then the next week you go to the other. But every so often, they were just like, yeah, I've got something to do today. Why don't we switch it up? And so they just reverse which one we were going to for that week. Or for, like, you know, we're going to switch today and tomorrow. Or we're going to do 2 calculus days in a row, followed by 2 physics days in a row. You know, that kind of... It was pretty interesting. But, they got, we got to the end of the semester, and then Dr. Black sent out an email to all of the people who were in my class and said, like, you're now invited to the next class. I have not even started Brainland. Nope, never read any of George Martin stuff. I don't know if I have as much patience for fantasy as I want to. I read, or I did the audiobook anyway, for Throne of Glass, and that was pretty cool. But I don't necessarily do fantasy anywhere near as much. Sci-fi is my jam, which is not surprising. And may I recommend, this doesn't come out in the United States until September, but nonetheless, Alien Clay by Adrian Tchaikovsky, amazing book. I actually want to work on a project to do something, but I'm inadequate. I am inadequate at the job I would like to do, so I need some more practice. But we'll see. Maybe I'll get some inspiration to do what it is that I want. Anyway, so Dr. Black sent out a thing that was like, anybody who is in this class who is interested, I'm doing an experiment, and you can come take your next 3 classes, which are differential equations, multivariate calc, Calc 3, vector calculus, whatever you want to call it, and linear algebra as one class. It is 12 credits over the course of 2 semesters. So you spend the entire year with 6 credit hours in your schedule, like all the way across, blocked out. I was like, this sounds interesting, let's do it. And the point was that he was going to teach all 3 classes to us over the course of 2 semesters. It was not separated, and so all of the well, you can't really do Calc 1 and but no, I understand. You did them consecutively, yeah. That seems a little difficult. Now, keeping in mind, Calc 1, 2, and 3 have different meanings in different places. Really what you want to say is, like, your Calculus 1 starts with the concept of the definition of derivative and limits and all that stuff. And this would have gone through my version of Calculus 1 ends with L'Hopital's rule and taking integrals, like basic integrals, as our last unit. Our Calc 2 starts with finding the integral between 2 functions, and then doing like rotational solids and things like that. And our Calc 2 ends with series and parametric integration and things like that. And Calc 3 then starts with vector calculus. I mean, it's just vector calculus, so it's partial derivatives and all that. Really? You gonna act up with me? Alright, fine. Just refresh the page, because I want to be a pain. Okay, cool. Anyway. So yeah, it really depends on what you mean by Calc 1, 2, and 3, but still, I understand. It gets rather difficult. Okay, especially if you're meant to take like 1 class per semester. Now you're taking 3. Alright, consider the following function on 2 variables. F of xy is equal to 3x squared y plus y cubed minus 3x squared minus 3y squared plus 2. Okay. For x between -2 and 2, and y between -2 and 3. Normally, our domain here could be defined just as xy belonging to, and then we could do it as -2, 2 cross -2, 3. Right, so most of the time we're going to refer to it as this crossing of 2 intervals. So all right, so Okay, so graph the surface and level curves on an appropriate domain, i.e. containing the above. In order to approximate the location of the local extrema or saddle points. That doesn't need a colon. Alright, so sketch level curves. Including enough contours to indicate the location and type of critical points graphed. Something like that. Ew, there we go. Okay. So one of the problems with this could be, like, how do you even go about doing that, right? One way is to use MATLAB, which is actually what he gave us code for it directly, because we weren't well versed in MATLAB at all. These days, MATLAB is maybe even not your best bet, but to do a 3D graph, it still does pretty well. Let me see if I can get... There is a particular... Yeah, if we use octave-online.net, usually we can do stuff like this. Hey, there we go. So we can get all sorts of stuff, including particular graphs. I'm not even sure that this code will work anymore because it is literally 20 some odd years old, but we'll give it a shot. So, all right, so x equals, let's try -2 colon 0.1, 0.1, colon 2, and we also need to back up here. We need to show more of the bottom. That'll work. So it does actually show the, there's more stuff up here to say, like, what's the answer, or what do we have stored as variables? But we'll just hang on to that for now. You know what? Hang on. Go back to Escaladraw. Undo, move. There we go. Okay, now let's just move to my minicam. A. Ugh. Boo. Alright, so here we've got this stuff. And then we could say, if we have this, then, right, octave 1 says x equals from -2 to 2, those are the end points on this, increment by 0.1. So we have included -2, negative 1.9, negative 1.8, negative 1.7, etc., all the way out to 2, positive 2. So 1.8, 1.9, 2. There are 41 items in that list. Okay, so then we say, okay, let y go from negative 2. I've got a cord in my way here. All right, go also 0.1 up to 3. And then we put a semicolon at the end to silence this because we don't want it to list it every single time. If you don't put that semicolon, it will print it immediately in this space here. So it takes up a lot of room. Then, no? I'm sorry, did you not like that? U comma v, so we're defining a vector. U comma v is going to be equal to mesh grid x comma y. So this is a 51 by 41 list that shows all of the points. U and v are vectors. I don't remember how that works. All right. What's u? So, yeah, it's like all possible points that are in there. Yeah, it's fine. Don't worry about it. All right, z is equal to, so this is our z function, and x and y are going to be the input values that we use for it, and the u's and the v's get us every possible, like, point on this 51 by 41 grid. All right, so z equals 3 times u squared, so we have to do dot to the second. What this does is it says take everything in u and square it individually. Rather than, if we just did u squared, it would try to multiply the vector u by the vector u, and that doesn't work. Or matrix. So a 51 by 41 cannot be multiplied by a 51 by 41. Right? The dimensions don't match. So in this case, we're saying, no, don't do dimensions and matrix multiplication. Just take this thing and square each individual number all throughout the whole throughout the whole matrix. Okay, and then multiply by v. And then we want to add v dot to the third, because again, we're taking all the values in v and cubing them. Okay. And then we said we want minus 3 times, we want x, so that's u dot squared. And again, like I said, this may very well already have like much better updates. I just don't know about them. Minus 3 times v squared. So v dot squared plus 2. And mute that so it doesn't print everything. Oh no. Where'd it go? Where'd it go? Times v. Dot times v. Same problem. Don't multiply the matrices, multiply the individual numbers. Alright, cool. Did it. So you notice that z is also a 51 by 41. Alright, we needed each individual value to be multiplied. Alright, so figure 1. Did not actually print it yet, that's fine. Okay, and then this says, let's do c comma h. It's going to be equal to contour x, y, y, z, comma 75. Uh-oh. Okay, there we go. C label. CHO. That's not a thing, is it? Ooh. Cool. Figure 2. Give me a surface for X, Y, Y, Z. Oh no! Ooh. Suppress large plot, 1 megabyte. Fine. Okay, so what we're doing here is we're going to say, like, this is the contour plot. We've got our 0, 0 here, right in the middle of that circle. So, Zarek, Kirby, hi, how's it going? Yeah, no worries. Okay, so we get our contour plots. And I'm just rough sketching this, by the way. Don't think that this is like a good version of this. Just going down here further. Okay, so we got like 1, 2, got 1, 2, 3, 4, give or take. Right. So we actually had -2 to 3 was what we were actually plotting in the y direction, and -2 to 2 was in the x direction. So this was telling us that we had asymptote, what looks like y equals 1. Right, and then contours above and below centered at 0, 0, and 0, 2. Yeah, we're doing all right. Did a long stream this morning trying to clean up the other crap around here. I have taken down several of the boxes that we had and put a whole bunch of my math stuff right here so that I can easily have some, you know, reasonably within reach a whole bunch of math stuff that we could put on stream, or we can use for inspiration, or just someday if I'm up here and like thinking about something and being like, I've read something like that, I can reach back and find it. So a whole bunch of stuff. There's still a whole bunch more stuff that I still need to get like situated. I have that green thing there is a rolling, used to house my desktop back in college when my desktop was like, you know, yay big. These days, my desktop is yay big, and it probably fits, but the heat management is not good inside of that thing. So it's pretty good for like a random shelf desk, you know, a bookcase, miniature bookcase, but that's about it. And my dad made it, so it's kind of cool. But yeah, got all of our stuff hanging out, all the painting stuff over here. Minis and things. Okay, so we got these in. There was also around -1 and x equals positive -1 is where it really starts coming together. Right, something like this. Roughly speaking, something like that. This was going up and over to the other side. Alright, we got the same on this side. They're slightly different from each other. But I don't know if that's just differences in the numbers that were used. It looks like they're approximately symmetric-ish. The bottoms are flattened out, the tops are rounded. Same deal on this side. So our contour plot looks, roughly speaking, like this, right? And so we want to say, all right, with this contour plot, what then is the rest of this going to look like? And what we're going to do is we're going to clear clear figures and give me a surface. Can you do it? There we go. No. Fine. Sometimes it's necessary, right? Oh, somebody clip it. Does that work? I don't even know. All right. Instead of a vector plot, do image SC. Yeah, it looks like it doesn't work. You might have to do it manually. I don't know how to do that, so let's see. Scale color. Fine, UK. Image SC XYZ. Maybe not, but worth a shot. Thanks. Thank you, Zach. By the way, this channel does need more does need more clips, generally speaking. So hey, anytime you feel like going back and watching some other stuff, and I think it can only actually do it on broadcasts. Like you can't do it on highlights, which are all that remain of the really old stuff. So I may have to actually go back and like rewatch some of my old highlight stuff, and then manually like download the video and stuff. Yay. Yeah, this is not what I wanted. I want a surface. Ugh. That. What's that? Surf Z, hold on, image SC. Okay. Ugh. I could also just make it fewer points. That seems like it might be less work. So if we go back to the beginning and say, okay, we're going to do this instead as maybe 0.2. We can have all of these things. Nope, nope, don't do that one. Just these? Nope. Okay. I don't know if I can do this. Oops. There we go. Worth a shot. Guess it. There we go. 0.2. 0.2. Bam. Alright, yeah, that's a lot less. Okay. And then we go with right, Z is equal to, oops, this one. Okay. Much nicer. CH contour. And then label, C label CH. Okay, so I mean, it looks basically the same. It's a little chunkier, so you'll notice like here, the lines are extrapolated, where it's just like, we're just taking the 2 points, or sorry, interpolated. We're taking the 2 points and we're just drawing a secant line between them. Whereas in the previous one, it was also doing the same thing. It was just that you couldn't see it because it was a lot smaller and finer. So in here, you can definitely see it because it's very coarse. I think these were also causing some problems right in the corners because there's just a lot of individual numbers that were being printed on there, and it was kind of unnecessary. But nonetheless. Okay, so then we do surf. Oops. X, Y, Z. A. And we can't actually interact with it. Cool. But you may notice this is exactly what I drew when I was 19 or whatever I was. So, right? It's a terrible rendering of the exact same thing. And it's not obvious where any of the local mins and maxes are, but using the contour plot above, we do know that we should have a, let's see, we should have saddle points somewhere around -1, 1, 1, 1. 0, 1 should have, well, it's nothing in particular, but it's between these 2 points. So it appears right. We appear to have saddle points near -1, 1 and 1, 1. Okay. And then we also appear to have local extrema at 0, 2 and 0, 0. Which ones are which? Again, you can go back to this plot here, and it appears, I suppose, like in this area there's a depression, so at which one's X, which one's Y? God, man, that's terrible. I think that this is our Y variable here, because our X variable here doesn't appear to have anything significantly like... I mean, it's significantly different if you go across, but yeah, it doesn't contain the minima and maxima just looking across. So I think this way is our Y's. So at X equals 0, Y equals 0, this appears to be a maximum. And at 0, 2, this appears to be a minimum, but it's really subtle. Not like super, super subtle, but fairly. So at 0, 2, I think we have minimum, and at 0, 0, we appear to have a maximum. At least it looks like it. Okay. So those 4 are going to be our critical points. And again, it appeared like we had close enough. Oh wait, right. We've got technology now. Can go like that. Bring that down a bit. Et voila, it's perfect. And actually, we were specifically looking for, further down this one. Right, this is asymmetric. So, -2 to 3. -2 to 2 along our x-axis. This is our positive y-axis. This is our positive z-axis. So at the corner, -2, -2, this was coming down to a local minimum, but only because it's the edge of the domain. So this one's down here. and it was low. So let's go like that. The values that we had at 0, 0 appeared to be somewhere around the like 30, no, 15, 20 range. Up to 40, down to negative 60. Oops. Hey. 100%, right there. All right, so this bottoms out somewhere over there near -2, -2. And then it's got a value of about just under there at 0, 0. So yeah, pretty close to here. And that was a maximum 0, 2. It appeared to be at a minimum. 0, 2 appeared to be at a minimum 0 or just under. Somewhere about here. It's pretty significant. Oh man. All right, pardon me for just a minute. Okay, so what were the other corners, right? So 2, -2 was also similarly somewhere about -60, -50, somewhere in that range. So 2, -2 is like here, also somewhere down this range. Get this going up like that and like that. Okay. Maxima on the corners are about 25, 30 for both -2, 3 and 2, 3. -2, 3, 30. And 2, 3, 30. Well then. You know. Somewhere around there. And then across the middle. Yeah, it looks like somewhat parabolic, hyperbolic, something like that. Both the top and the bottom there. Okay. Something like that. Alright, and then to do contours, right, this is gonna come down like that, go up like that, down like that, give or take. When you start doing Calc 3 stuff, you generally speaking have to be kind of careful, because a lot of the times, students have never done this before, right? They've never drawn real, like, actual three-dimensional objects. It's always like, I'm just gonna draw a square, and then another square behind it, and then connect them, because that looks like a cube. And, like, okay. Sure. But let's also, you know, learn how to draw a real three-dimensional object with a mesh grid on top of it. Right, so, et voila. It doesn't look great, but, you know, this is my approximation of the thing we just created on the other page. So, alright. See you, Kirby. Good luck. Have a good sleep. Congratulations on finishing. So anyway, this is the kind of thing that you'd actually show. You see stuff like this all the time, especially if anybody plays, like, you know, golf video games. You've seen the mesh grid before. It tells you how the green lies, and, you know, if you're putting, which way is it going to break and things like that. And you can read it just in your own mind, thinking about it. Be like, ah, I understand intuitively how this is going to work. It's going to kind of swing around this way and do that and the other thing. You see these all the time, those of you who have, you know, relatively decent vision or corrected vision. You could just see this looking at the ground, right? If I were to roll a ball, where's it going to go? This is also used on a lot of our approximations for space-time, right? How does how does an object move in the presence of a gravitational field? It can be approximated by a mesh grid on a two-dimensional plane. Or using a mesh grid on a three-dimensional surface to represent gravitation on a two-dimensional plane. Because usually they're using the rubber sheet model, which is not entirely accurate. It's, again, more... I've seen some really cool ones where the like three-dimensional spacetime actually gets pulled into the planet. There's just always more mesh grid coming in from the edges. It is a pretty nice one. Anyway. So with this, we appear to have these saddle points. Again, -1, 1, 1, 1, and local extrema, a minimum at 0,2 and a maximum at 0,0. At least we think so. It looks like that based on the surfaces that we got. Okay. I will say I did better with this one than I did in undergrad, but that's not really surprising. Okay. B. Find the location of those critical points algebraically. Alright, so algebraically, what we're going to be doing is we're going to say find those critical points algebraically. How do we do it? Oh, well, of course, it's like everything else that we've done. How do you find critical points in just regular calculus? You set the derivative of the thing equal to 0. The difference is that in this particular case, we've got a vector field. So it's a function in multiple dimensions. So how do we find the rate of change of the entire thing? Well, there is a function. You can either call the del function or, oops, no, not that. The del function, where we say, okay, we're going to take this derivative operator on f being a multivariate function, xy, and set it equal to 0. But it's not just a derivative, right? In this case, derivative of f on xy as a multivariate function ends up being the ends up being a vector where we take the partial derivative with respect to x and the partial derivative of f with respect to y. Unless I completely screwed it up, but hey, it's always possible. Yeah, cool. I also have put the vector notation over the operator. So if anybody wants to... Oh, yeah, right. That's equal to the 0 vector. If anybody wants to yell at me about this, please let me know. I think it's good, but... So in this particular case, we've got our f of xy, it's going to be equal to, recopy from the top, 3x squared y plus y cubed minus 3x squared minus 3y squared plus 2. So partial f with respect to x is going to be equal to, here what we're doing is we're saying, okay, the partial derivative is going to treat only x as a variable. All other variables are going to be treated as constants. So y in this case is just a constant. Okay, well if y is a constant, how do we take the derivative? This is going to be 3x squared times a constant is just 3 times a constant, or a constant, like 3 times another constant, times x squared. So you take the constant out, it's just 3y, times the derivative of the x part. So the derivative of x squared is going to be 2x. Plus the derivative of y cubed with respect to x. It's a partial derivative, so we treat y as a constant, so the derivative is 0. Minus 3 times, again, x squared becomes 2x. Minus 3y squared, again, it's a constant, so it's 0. Plus 2, it's a constant, so it's 0. So we're taking like all this at once as a constant, and we take its derivative, it's 0. Right, if we wanted to, we could actually physically move stuff to be like, here are all the constants, and here's all the stuff with x's. So the partial of f with respect to x is going to be equal to, this is 6xy minus 6x. So partial f with respect to x. And then we want partial f with respect to y. Now do the same thing, but now treat y as the variable and x's as the constant. So in the first term, 3x squared is constant times y, take its derivative, is just 3x squared. Plus, take the derivative of y cubed with respect to y is going to be 3y squared. Minus 3x squared, it's a constant, so it's 0. Minus 3y squared. Y squared is not a constant, so that's going to be, again, 3 times here, 2y. Plus 2 is a constant, so it's 0. Take the derivative, it's 0. Alright, partial f with respect to y is then going to be equal to 3x squared plus 3y squared minus 6y. So, I tapped that. So taking it all together, del f of xy is going to be equal to, and actually, right, this is going to be called the gradient. So we're taking the derivative of all these pieces. We're saying, okay, what's the vector that we're going to get on at any particular location, anywhere in the entire surface? Plug in a particular xy. What is the vector of steepest descent? And in fact, we can just say, like, you know, anywhere you want to go on this. What's the what is the vector of steepest descent at any particular location? That will get us the surface, or at least get us the, like, motion of what a ball would do on the surface. If I'm not explaining it correctly, feel free to roast me, because quite frankly, it's been a long time. Alright, so this is going to get us a vector of 6xy minus 6x, comma, 3x squared plus 3y squared minus 6y. And we want this to be equal to 0, a 0 vector. So we need, in this particular case, we've got a system of equations now. So 6xy minus 6x equals 0, and 3x squared plus 3y squared minus 6y equals 0. So system of equations, or simultaneous equations, or whatever you want to call it, it's all the same stuff. Both of these things need to be true at the same time. So here we've got 6x as a common factor, and y minus 1 is what's left, is equal to 0. So either x equals 0 or y equals 1 is going to get us a 0 in either of these places. If you need that broken down, you probably shouldn't be in Calc 3. But if any algebra students want that clarified, I can clarify it. Okay, so over here, 3x squared plus 3y can be pulled out of this stuff. Maybe it's not the best idea, but whatever, it's fine. 3y times the quantity y minus 2 is equal to 0. All right, so in this case, what we can do is say we've got two contingencies now. Either x is 0 or y is equal to 1, or both. If we've got both, we want to verify that that is actually possible over here. So if x is 0, we get a 0. If y is 1, we end up getting 1 minus 2 is a negative 1, is going to be a negative 3. So negative 3 equals 0. So no. Immediately, 0, 1 is not possible. So this actually moves to exclusive OR. We can't say that both are going to happen at the same time. We said if x equals 0 and y equals 1, our first equation works fine. Both parts are 0. 0 times 0 is 0, so we're good. But the problem is that when we go to the second equation, we end up with a 0 plus 3 times 1 times 1 minus 2 is equal to 0. Again, this is going to be a negative 3 is equal to 0 is not true. So it has to be exclusive or either x is 0 or, and not both, y is equal to 1. So if x is equal to 0, then we've got 0 plus 3, might as well just factor, it's fine. 3y parentheses y minus 2 is equal to 0, so therefore 3y times y minus 2 is equal to 0. So then y equals 0 or positive 2 are going to be our possible solutions. So when x is 0, y is either 0 or 2. Okay. And in the exclusive part of this, y equals 1 is going to get us 3x squared plus 1 squared minus 6 times 1 equals 0. We're just not going to go through the factorization of that because we don't need it. Oi. I feel something rattling. I'm just trying to get rid of it. Alright, 3x squared plus 3 minus 6 is equal to 0. I mean, really, we already knew what this was going to be anyway, but it's fine. All this stuff, add 3 to both sides. And we get x squared is equal to 1. Yeah, you could divide by 3 all the way across and clean that out. Alright, so that means that the absolute value of x is equal to 1, which means that we've got two locations again. 1, 1, and negative 1, 1. There it is. Here we've got 0, 0, and 0, 2. So now we've accounted for all 4 points that we were talking about up above. These are the critical points. 0, 0, 0, 2, 1, 1, negative 1, 1. That doesn't classify what they are, but nonetheless, those are our first derivative critical points. All right, part C says, so can we make a second derivative test equivalent for vector calculus? So it seemed to me that we should be able to say, okay, sorry, no. Not equal to null. All right, so find out where these points are going to be 0, 0 vector, are going to get us a the inflection points. And if we have our second derivatives with respect to x and y having the same sign, then this should be a concave either up or down, depending on what sign it actually is. Right, non-zero. So that's our second option. Our third option is that these things could have opposite signs. U. In which case, we're going to get that it's curving downward in one direction and upward in the other. This is a saddle point. All right, and then this is when they're both the same, right? When they're equal to each other. This is when we end up with inflection points. So this takes care of 3 of our possible options, but there's a 4th, right? The other option is that only one of them is equal to 0. Or equal to the 0 vector. Exclusive or. So when both of them are equal to the 0 vector, we end up with inflection points. If they're both non-zero but then have either same or opposite signs, if they're the same, it's concave up or down depending on the sign. And if they have opposite signs, it's got to be a saddle point. And then the only fourth option left is, okay, what if it's one of them, exactly one of them, is 0? And that's going to get us no motion in one particular direction. So we have no motion in the x direction. It just continues out like this. It's flat. And then it's going to be changing in the y direction. That leads to like some sort of some sort of flat area that curves on both sides. I don't know how to exactly explain that. There's a... It's not like a... Oh, like a plate, I suppose. No, because that's in both directions. It's flat. Like a gutter, maybe? If like a gutter came down to... rather than a flat bottom, literal flat bottom, if it was just like a parabola or something like that, right? This would come together like that, and then the bottom is just flat all the way across in one particular dimension, whichever one it is. So, oh, trough, right? Yeah, like an animal trough. As soon as I start drawing it, right? You don't necessarily want something to, like, sit in the bottom, if that were the case. Or like a pipe, right? A pipe can have a 0 curvature in one dimension. Right, if that was closed there. Right, so then where does that happen? Well, we've got to take the second derivative of the thing we just had. So we had here, first derivative. Six xy minus 6x by 3x squared plus 3y squared minus 6y. Right, and then we want to do, what about the second derivative of f? So we're going to take our first derivative with respect to x and take it with respect to x again. So this is going to be 6y minus 6 by, and again, take our first derivative in the y position and take its derivative with respect to y. So 3x squared becomes 0. 3y squared becomes 6y. Minus negative 6y becomes minus 6. So, that's interesting. The second derivative with respect to each individual direction is identical to each other. It's just 6y minus 6. So they are going to be identical, which means that where they are 0, they are 0. They're both 0. And where they're not 0, they're both not 0. They're also independent of x. Is when y is equal to 1. And this is also independent of x. So as we go across y equals 1, we did actually see that the y equals 1 going across here, we did see a break between these things. This is what I termed the asymptote between them. Here, y equals 1. So our gradient or curvature in the y direction is 0. It is flat at that particular, along that particular line, y equals 1. Okay. All right, this is flat or it has no curvature. And then we have to say, okay, if we're going to take this and then go back to this stuff, we're going to say, okay, we're going to use 0, 0, and that gets us a -6, -6. So, let's see. Let's use a different color. This is going to be del squared f is equal to -6, -6. For 0, 2, it's independent of x again, so that just goes away. And then we get a, right, 6y minus 6, so y is 2. So that's going to get us a 12 minus 6 is going to be +6, +6. Okay, and over here, 1, 1 is going to end up with a... Oh, that's weird. That shouldn't happen then. Huh. The only thing that's different here is our x values. Oh, but y is equal to 1. Right, okay. Right. If y is equal to 1, then we end up with 0, 0. In both of these cases. Right, yeah, okay. So this is concave down, meaning that the one at 0, 0 should be a maximum, and the one at 0, 2 is concave up, which is then going to give us a minimum. So maximum, minimum. All right, and then over here at 1, 1 and negative 1, 1, again, this is flat. So I was even wrong about there being saddle points here. These are not saddle points. They're just flat. I guess we could like check to either side of it, up and down, and see what exactly is happening, but I think we know what that is. So we've got, according to this, right, if we just go slightly above y equals 1, then everything is curving back in order to start moving up again, so it's going to be concave up, and everything just slightly lower. It's not lower. Everything slightly with lower y values than 1 are concave down. So they're still going up, but they're accelerating downward, curving downward. So let's see. It seems that y equals 1 is a perfect inflection point at this point. It's not saddle, because you'd have to have opposite curvature in either of the orthogonal directions. So no curvature in x direction. Concave up when y is greater than 1. Concave down when y is less than 1. So like this is sort of an inflection line. That's the best we can do for an analogy anyway. Alrighty. If anyone has any questions, please let me know. Alright, since we also streamed a bit, quite a bit earlier, I think that's probably going to do it for me, but we will head on over and see, I think probably Dawn, because Dawn does math. He may be just about ready to go, though. see how he's going. So I do want to thank you, everybody, for coming around, for sticking around, having some fun tonight, and having some fun possibly earlier today, if you were in earlier today. Thank you for coming. And I will probably be back doing some more accountability streaming tomorrow. Or not, we'll see. Have fun, everybody. Have a good night. This is Obi-Wan Pez for N Simplex Pachinko. See ya.